Okay, so we're picking up with our work on the L'Hopital's rule, and we're looking at question D here. In question D, we were looking at the limit as x approaches infinity of e to the x over x squared. Okay, so I'm just going to jot this down here so it's a little bit larger. We get the limit as x is approaching infinity of e to the x over x squared. And so one thing I want you to get in the habit of is identifying whether or not a limit has an indeterminate form to it. Okay? Well, if you were to do direct substitution on this, which is illegal in this case, but if you were to do direct substitution, we'd find out that our numerator is approaching an arbitrary large number. That is, as x gets large, what happens to e to the x? It approaches infinity. And as x squared gets large, what happens? Well, it approaches infinity as well. So this particular problem has the indeterminate form infinity over infinity. Keep in mind, those were one of the two indeterminate forms for which L'Hopital's rule applies. Okay. So we're going to go ahead and take a look at this. I can't find out any other means for evaluating this limit, so I think it is a good idea to apply L'Hopital's rule. So that says that this particular limit is equivalent to finding the limit as x approaches infinity of, and now I'm going to take the derivative of the numerator over the derivative of the denominator. That's what L'Hopital's rule is saying. So this comes out to be the limit as x approaches infinity of e to the x all over 2x. Okay? But this is similar to the first example that we looked at, and here's the bummer. This still has the indeterminate form infinity over infinity. So does that mean we made the wrong move? Did we go the wrong route? Well, maybe it does. I mean, if the problem doesn't get any simpler as you apply L'Hopital's rule, then maybe it's not a good idea to do so. But in this case, I would argue that we're actually on track, because originally we had a quadratic in our denominator, and now it's down to a linear function. So this still has indeterminate form infinity over infinity, so I think I'm going to go ahead and apply L'Hopital's rule a second time. And we end up with the limit as x approaches infinity of e to the x over 2. Again, how did I go from this line to this line? I took L'Hopital's rule a second time. How do I know that? Because I annotated my equal sign with an LH there. Well, what can we do with this? Well, no longer do we have an indeterminate form. Now, it's very important we not apply L'Hopital's rule a third time because it's not appropriate to. We no longer have an indeterminate form, but luckily we're down to something that we can evaluate through elementary means, meaning we've got just a single expression here, 1/2 e to the x, or e to the x over 2. And what's happening to the expression? Well, x is getting large, and so it's going to be approaching infinity. Okay. So I'd like you to go ahead and pause the video and try this for letters E. Go ahead and try it for letter E. So pause the video and then pick it back up. Okay, so hopefully you've worked through this and you saw that the answer came out to be -6. If you didn't get that answer, go ahead and keep working on this problem. Try to get that correct work. Now notice I haven't shown you the intermediate steps here. So you do need to fill those in to get full credit for your pre-work. So the answer comes out to be -6, but you need to be able to get there using the appropriate limit tools. Okay, let's look at letter F here. I'd like you to pause the video and try letter F and see what you get. So go ahead and pause the video and work through it and figure out what you get. So one thing that's very easy to do after you've learned the L'Hopital's rule is it's to start applying it in places where it doesn't work. So let me show you a common mistake that students will make on this problem. A common mistake would be to go ahead and say, well, this is equal to, through L'Hopital's rule, the limit as x approaches pi of the cosine of x all over minus the sine of x, taking the derivative of both the numerator and the denominator. And then I'm not sure what. Maybe at this point you would conclude that the answer, you'd have to do left and right hand limits, and maybe you come out with the answer the limit does not exist, or you say it's something like plus infinity from one direction, minus infinity from the other direction. It doesn't matter because you made the wrong first step. Why did we make the wrong first step in this question here? Because right off the gate, we went ahead and applied L'Hopital's rule to this problem, and L'Hopital's rule doesn't apply in this case. So let's go ahead and look at this problem a little more carefully, and let's see if we can evaluate the limit. This is not an indeterminate form. Okay. It is true that the numerator of this function is approaching 0, but the denominator of this function is actually approaching 2. Okay. So in fact, this limit, even though I put it in the L'Hopital's rule section, is one that can be evaluated using other means. And in this case, we'll just go ahead and do direct substitution on this limit. We get the sine of pi all over 1 minus the cosine of pi, which is equal to 0 all over 1 minus a minus 1, which is equal to 0 over 2, which is of course equal to 0, and that is the limit for this function. Notice that I never applied L'Hopital's rule. We never used L'Hopital's rule in this problem. Okay? So above we see that we need to confirm that we have an appropriate indeterminate form before applying L'Hopital's rule. I guess I've already got the apostrophe S there. Before applying L'Hopital's rule. Okay. Now, let's jump back to our original statement of L'Hopital's rule, where we said if you have a differentiable functions and you have an indeterminate form of 0 over 0 or infinity over infinity, then we can go ahead and apply L'Hopital's rule. Okay. And that's what we've done here. Let's see here, in question number A, we had indeterminate form 0, 0. In question number D, we had indeterminate form infinity over infinity. But what if we have a different indeterminate form? Well, we're going to learn rules or methods for handling other indeterminate forms. Okay? So let's suppose we have an indeterminate product. Okay? This isn't an indeterminate quotient like 0 over 0 or infinity over infinity. In this case, it's a number like 0 times infinity or 0 times negative infinity. So if our limit has that general structure, the trick is to rewrite the given product as a quotient. That is, suppose we have two functions being multiplied together, we can go ahead and write this as f divided by 1 over g, or g divided by, let me make it a horizontal bar, g divided by 1 over f. Okay, so in either case, what did I do? Well, in the first case, for my quotient, or for my product, I went ahead and brought g below the line, and when I did so, I had to invert it. Or in the second case, I went ahead and took f, the factor of f, I took it below the line, and when I did so, I had to invert it. That's just like if we had 3 times x, we could rewrite this as 3 divided by 1 over x, where I take the x down and invert it. Or if I had, say, 7y to the second power, I could rewrite that as 7 over y to the minus 2, taking it below the line and inverting it. So let's go ahead and practice that on example A here. Here we've got the limit as x approaches 0 of x times the natural log of x. So let's identify the structure of this. Okay. This happens to have the indeterminate form. Well, let's see here. As x approaches 0, what happens to this first factor of x? Well, as x approaches 0, that first factor of x approaches 0. So this has indeterminate form 0, and then as x approaches 0 from the right, what is the natural log of x approaching? It's approaching negative infinity. If you've forgotten that, remember that your natural log curve looks like this. So as I approach 0 from the right, my y values are tending towards negative infinity. So this has the indeterminate form 0 times negative infinity. Just as a reminder, L'Hopital's rule doesn't immediately apply to this problem, even though 0 times infinity, or plus minus infinity, is an example of an indeterminate form. So let's see how we're going to tackle this. So my rule of thumb is when you have one of these indeterminate products, rewrite it as a quotient. So here we're going to take this limit that has the indeterminate form, 0 times negative infinity, and I'm going to go ahead and bring one of these factors below the fraction bar. So I'm going to bring x below the line. Now you can't just bring a factor below the line. If you bring a factor below the line, you also have to invert it. Well, notice that this now has the indeterminate form, negative infinity over infinity. Because the numerator factor, that's this ln of x term right here, that numerator factor is still heading towards negative infinity, and now the denominator factor, it's no longer x, it's 1 over x, and as x approaches 0 from the right, that tends towards positive infinity. So now that this has the correct indeterminate form for which the L'Hopital's rule applies, let's go ahead and do it. Then this gives us the limit as x approaches 0 from the right of, what's the derivative of the natural log of x? It's 1 over x. All over, what's the derivative of 1 over x? It's minus 1 over x squared. Now is the time to make a really important point. Notice that this still has indeterminate form. In this case, it has indeterminate form infinity over minus infinity, but don't keep using L'Hopital's rule. L'Hopital's rule is a powerful tool, but it's not always the best tool in a given circumstance. In this case, even though I could keep using L'Hopital's rule, because it still has one of the appropriate indeterminate forms, I think I'm just going to go ahead and simplify this limit through algebra. So if I went ahead and now take this term and invert and multiply it, I'm going to end up with negative x. So again, what did I do? I went ahead and inverted this 1 over x squared term to multiply to 1 over x. Let's just show that. So this would be 1 over x times negative x squared over 1, inverting and multiplying as we do for fractions. And so then we're left with the limit as x approaches 0 from the right of negative x. This limit is now ready for direct substitution, and it comes out to be 0. All right. Let's go ahead and do letter B here. So letter B, we've got this product here of 2x and e to the 3x. So doing the, looking at the form of this, if we were to do direct substitution, the first factor, the 2x factor, is heading towards minus infinity. Okay? But the second factor, e to the 3x, if we plug in a large negative number, let's see here, the graph of e to the 3x looks like this, and as we go to the left, my y values are tending towards 0, so this has the indeterminate product, negative infinity times 0. So this has, as I said, the indeterminate form, negative infinity times 0, so let's go ahead and rewrite it. That's what our rule of thumb says. It says if you have, again, that's this rule right here, if you have an indeterminate product, try to rewrite it as a quotient. So in this case, what I'm going to do is I'm going to take the 2x, I'm going to keep it above the line, and I'm going to rewrite this as e to the minus 3x. What did I do there? I brought the e to the 3x below the line, but then I also inverted it. Okay. So now this has the indeterminate form. This is still heading towards infinity, and now my denominator is also heading towards infinity. So it says the indeterminate form infinity over infinity. So now we apply L'Hopital's rule, and we get the limit as x approaches negative infinity of just 2 over negative 3e to the minus 3x. Now, if you want, you can rewrite the original problem, or rewrite this limit as minus, that's not true, as 2e to the 3x over 3. It doesn't matter. This is tending towards 0 now. Okay. Why is that? Because I plug a large negative number into e to the 3x, that approaches 0, multiplying that by 2/3, and it approaches 0. Okay. So I'd now like you to try letter C on your own. Go ahead and work through that, and I'll give you the answer when you're done. Okay. So for this one here, we would have found the limit to be 0. Okay. Again, please, folks, if you're skimming through these notes as quickly as possible, you have to fill in the work here. Show me the work that gets us to that limit of 0. Alrighty, that's all I've got for this video, and you've got one more for the pre-work.